Start the recording. Okay. So welcome to week 3 of Electromagnetics and Guided and Wireless Media course. And I'm Shazam Bhatt. And this course is being offered by Professor Pradeep Kumar from IIT Kanpur. And what we are going to see today is week 3 module, which has been covered on the NPTEL. And we are going to look at some of the examples of lattice diagram, as I received some of the queries that I skipped some of the questions in the previous week because of the time restriction. And maybe I'll take a couple of questions from that week, but specifically related to lattice diagram and its application in the circuits. And today, what we are also going to see its applications in the circuits, and we will just move forward from it. Then we'll be briefly jump into the electromagnetics part, which is basically the electromagnetic waves, its propagation, which is, I should say, the basic fundamental electromagnetic wave course portion that has been basically covered in this week. So this session will be slightly different. I'll just briefly try to describe some of the things Professor might have discussed. I don't want to repeat that, but maybe I'll just give you some little more details which are necessary, maybe for your courses, for examinations, or for if any of you are interested in research. So I'm going to turn off my camera for now, and I'm going to switch my device. So we will start here. And let me just briefly talk about, okay, so just briefly, so let me just briefly talk about what has been covered in this, which is in this week. So in the previous week, we talked about something called as lattice diagram. And in it, we basically talked about how we can use this lattice diagram to determine, let's say, specific time delays in a circuit. Okay, and when we are talking about time delays, we are talking about transmission line, let's say something which looks like this. This is the source part. Let's say this is some sort of a voltage. This is the source resistance, and then you have a transmission line that goes to the maybe load end, and this has a intrinsic impedance of Z0. So we talked about that once. If you, let's say, give some sort of a signal to this end using the source, it's going to traverse to the load, and because of the impedance mismatch, it's going to reflect back in time 2 TD, and then it will come back in time 3 TD, and it'll go back in time, let's say 4 TD, so on and so forth, 5 TD. This is sort of a back and forth reflections from the source end and from the drain end. And why does those reflections occur? Because of the impedance mismatch. So you have been talking about these impedance mismatch a lot, and this impedance mismatch is basically controlled by a parameter which is called as reflection parameter. So you can have a reflection from the load end, you can have a reflection from the source end. Okay, so reflection from the source end will depend upon the source resistance minus the characteristic impedance divided by source resistance plus characteristic impedance. From the load end, it will depend upon ZL minus Z0 divided by ZL plus Z0. So this is the impedance mismatching. And this impedance mismatching determines how much voltage will be basically, what is happening? This is not good. So it determines that how much voltage will be present at the source and the load and once it's basically reflected. Okay, so that's what we basically talked about. Now, if we let's say take an example, maybe for example, if we have till now you are considering DC voltage sources, just to make sure that we are not right now going into the AC. Maybe down the line we will go into the time varying sources as well. So this particular symbol is not exactly right. It should be a DC source. And whenever you basically show plus minus, it's basically a DC source. And this represents a time varying source. So this is a time varying source. Okay, so I don't know what's happening. This is a time varying source. And now If we talk about, let's say, for example, you have a circuit like this, which is basically having uh, maybe a load ZL, and this is having impedance Z0, and let's say this is some voltage V. And let's assume as has been discussed in the slides, for example, the source resistance, which is basically this resistance, is 2 times the Z0, basically the intrinsic impedance. So this is the intrinsic impedance of the transmission line. And let's consider Vs to be equivalent to 45 units u times unit step function. That means it's something like this, which is basically 45 volt at time t equals to 0, and it is limited. It's sort of a step function. Okay, and once we do it, we can basically have the load resistance. Let the load resistance will be let it be half of the intrinsic impedance. Once we know this, we can compute basically the reflection coefficient, which is basically given by this thing. It will be minus 1 by 3, and the the reflection coefficient from the source end, that is from this end, once the once you give the step function to it, it's going to traverse here, it's going to reach this load, and then it's going to get reflected. And the reflection coefficient from this source will be again so that it will go back to the load. So that reflection coefficient will be equivalent to plus 1 by 3. You can compute it simply by using this particular uh, equation. Okay. And now what is going to happen? Now you're going to compute the V1 plus, which is basically voltage at time t equals to 0. So it will be equivalent to basically it's a distribution network. So there are two resistors in series. So the voltage will be divided. So it will be Z0 divided by 3 Z0 plus into 45 volt, which is basically the initial volt. So it'll be around this goes. So it'll be 45 by 3, that is 15 volts. So this is V1 plus. Okay. So now what is basically going to happen? So now you draw the lattice diagram, which is basically the time axis, and this is basically the space axis. So this is the space Z. So this is Z equals to 0, this is Z equals to L in a transmission line. And this is, let's say, let's denote some of the points. Let's call this TD point. This is, let's say, 1, 2, 3, 4, 5. So this is basically T over TD, not only T. That's why this is basically at time t equals to td. So this is 2 td, this is 3 td, and so on and so forth. So this is basically something called a normalized time. It's normalized with respect to the delay time. Just remember that it's never only time. That's why you can write 1, 2, 3, and 4, and so on. Now, what's going to happen? Once you now basically have a at time t equals to 0, you now have a voltage which is basically 15 volts at the load end. So now it is going to rise up to the 15 volts. This particular load is going to have a voltage of 15 volts. Remember that this is the load end and this is the source end. Okay, so at particular load at this time TD1, basically at time t equals to TD, this will be equivalent to 15 volts. Okay, now because of the reflection, the voltage will go, it will, the voltage, whatever voltage we have given, it will go back to the source. So it will go back to the source. Now, how to compute the value, how much it will be? So if this is 15 volts, this will be exactly 15 divided by 3, but with a negative sign. So it's exactly gamma L times 15. Okay, and gamma L is minus 1 by 3 times 15, so it will be minus 5 volts. So this is exactly minus 5 volts towards the source end after time 2 td. Now it will come back towards the load end. But how much will it be? It will be minus 5 by 3. So how can we compute it? It will be this particular coefficient, which is plus 1 by 3 times minus 5. So it will be minus 5 by 3. So here it will be minus 5 by 3 volts towards the when it will come towards the load end. And again, now it will get reflected towards the source end, and again the voltage will be divided again by 3. So this number, that means minus 5.3, which is around maybe minus 1.63, it will be again divided. So it will be, so now the minus sign will be again, so it will be minus 1.63 times minus 1 by 3. So it will be 1.63 divided by 3, that is around maybe 0.55. Okay, So it'll be 0.55 volt. So there'll be no negative sign again here. Now it'll again get reflected, and after time 5 TD, again it will be divided by 3, so it'll be 0.21. So it'll again stay positive because it will be 0.55 times this thing, which is 1 by 3. So it'll be around 0.21. And then it'll again get reflected. But approximately after 5 TD, we assume that it reaches the steady state value. So this is basically 5 TD. This is basically the lattice diagram, which in simple sense is it's not necessary to make the lattice diagram. You can just compute these things from the reflection coefficients from the source and the load end itself. It's not necessary to make this lattice diagram even, because it's simply the multiplication, back and forth multiplication of the source reflection coefficient and the transmission and the load reflection coefficient. Now this thing can be shown in a plot where you can basically plot the voltage at the load end as a function of time. So this is a function of time. At time t equals to 0, you don't have any voltage at the load end because it takes time td to reach the load end. Okay, it takes time td. This time, it takes time td to reach the load end. So your time will be td. Let's say, let's write 2 TD, let's write 3 TD, so on and so forth. Now what's going to happen? Between 0 to TD, there will be no voltage at the load end. So the voltage is going to arrive after time td, so it will rise. Okay, it's going to rise to a particular value, and then what's basically going to happen? So what will be this value? This will be 15 volts. After time, now when is the voltage coming back towards the load end? It's coming after time 3 TD. Okay, so this is the time after which it's again coming back. So this is the first time instant, this is the second time instant, and this will be the third time instant after which the voltage is coming back. So these 3 time instants are basically being plotted on this VL versus time curve. So first you get to 10 volts, then it will stay at the 10 volts. Then after time 3 TD, what's going to get, it's going to receive another minus 1.67. So it'll be minus 1.67. So it'll drop by minus 1.67. So it'll be slightly down. Then it will stay at that particular value. Then again at 5 TD, it's going to receive another value where it's slightly increasing from this value, and it's going to stay like this, and then it will be nearly constant after a certain 5 time TD. Okay, so if you sort of look at this particular curve, it's looking something like this, and then it's stabilizing. Okay, so it's sort of a initial transient, which is basically uh, sort of a time varying initially. It's basically not stable response, and then it basically tends to stable response. It's sort of a something whatever you might have studied in the control systems as well. Okay, after a certain time constant, which is 5 TD or 6 TD around, depends upon the system, and also depends upon how much is the reflection. Yeah, it definitely depends upon the impedance mismatch. So that is the response of this particular system. Now, what is going to happen? What's let's take one more example. If we say, let's say, if we have, for example, this particular example here, which was basically given in the which was basically one of the questions from the week 2, I guess, wherein you had to compute these particular parameters using the lattice diagram. You had to determine the voltage at the source and load at time t equals to 4 microseconds. So now whatever TD and T values you have been using, basically you now have to use the realistic values. Okay, so let's understand this question. In a transmission line of length 100 meter with a phase velocity of 10 to the power 8 meter per second, characteristic impedance, which is the intrinsic impedance, is given, and the source resistance is given, and the load resistance is given. The line is charged to an initial voltage V equals to 160 volts. That means it's constant DC volt at time t equals to 0. Now using the lattice diagram, we'll have to determine the voltage at the source and load at this particular time. So you need to determine voltage at source, voltage at load at time t equals to 4.5 microseconds. So this is basically the unknown quantity which we need to compute. Okay. So if we can draw this particular figure, it will be something like this. This will be the source resistance, which is 50 ohm. Then there will be a intrinsic impedance, which will be 100 ohm. And then there will be basically some load here, which is ZL. How much is that? It is basically 200 ohms. So it's only a resistive network. That makes it simpler. Okay, there is no capacitance or inductance. And then you have a source, which is sort of a DC source that is around 160 volts at time t equals to 0. And what else is given? Or you are also given the phase velocity, which is 10 to the power 8 meter per second. I have not discussed the difference between the phase velocity and group velocity. Maybe you might get to know about these things in the upcoming weeks, where we will discuss about these in detail when we talk about the electromagnetic wave properties. Right now, just treat it as a velocity of this particular wave, which is not true, but just treat it like this with the velocity with which it is moving through the transmission line. But it's not exactly that. Let's just simplify it for the time being. And now, what else? What else we are given? That's it. So now the first thing, first and foremost thing in these questions is to compute. Basically, first thing you should compute is basically the reflection coefficient at the load end and reflection coefficient at the source end. So the reflection coefficient at the load end will be, how much will it be? It will be, let's compute first reflection coefficient at the source end. It will be exactly 50 minus 100 divided by 50 plus 100, which is basically the source resistance minus the intrinsic impedance divided by the summation of that. So it will be minus 1 by 3. Now at the load end, how much it will be? At the load end, it will be 200 minus 100 divided by 200 plus 100. That will be 1 by 3. Okay. Also, one more thing to compute is basically the time delay. How much time this particular voltage takes to get to the load end, which is basically time delay TD. How much this TD will be? It's simply given by the length of this transmission line divided by the velocity you're given, which is basically the phase velocity. Okay, and how much is the length? Length is given as 100 meter divided by 10 to the power 8. So you compute it, you get around 1 microsecond. So when you just close the switch at time t equals to 0, the switch is closed. It's going to take around 1 microsecond for this voltage to appear at this load end. So 1 microsecond it will take, which is not a huge time, but it makes a lot of difference in the circuits. This 1 microsecond is a huge time in terms of the circuits you're operating, because they work in nanosecond regime. They work super fast, maybe 100 nanosecond, couple of nanoseconds. And if it's taking 1 microsecond, then it's a huge delay that's going to be basically incorporated in the circuit. So that's why it's detrimental. 1 microsecond may sound small, but it's a huge time. And now what's basically going to happen? We can draw a lattice diagram. First of all, maybe we can compute the voltage, or let's simply draw the lattice diagram. So we can draw the lattice diagram like this, wherein you have the time t over td. This is the z. This is z equals to 0. This is z equals to L. So you have td equals to 1, 2, 3, 4, 5, and so on. So this is 1, 2, 3, 4, 5, and so on. Now, at time t equals to 0 and at time t equals to sorry at z equals to 0 and z equals to L, initially the voltage at the towards the load end is going to rise up to how much? The 160 volts. So it will be 160 volts towards the load end at time t equals to TD, and then it's going to get reflected towards the source end. And now, how will you determine how much it's reflected? It will be how much will be reflected? 160 into 1 over 3, this particular coefficient. So it will be 160 over 3. So this will be 160 over 3 volts. Now it will again reflect back towards the load end. How much it will be? It will be multiplied by this coefficient. So it will be 160 by 3 multiplied by minus 1 by 3, which is minus 160 divided by 9. So it will be minus 160 divided by 9 volts. Now it will be reflected here. Yes, you have a question? Hello, you have raised your hands. Okay, let me just continue. Maybe it's a mistake. So it will be reflected, and it will reach towards the source end in 4 TD. Again, it will be reflected from the source towards the load end. And how much will be the value? It will be minus 160 over 9 into minus 1 by 3, which will be plus 160 divided by 9327. Okay, that will be, oh no, okay, I have missed this. This thing is basically here. So once it gets reflected towards the uh, source end, it will be 160 divided by 27. Again, it reflects back. It will be 160 divided by 81, which is basically 160 divided by 27 into 1 by 3. So this will be 160 divided by 81. So this will be 160 divided by 81. Again, it gets reflected towards the source, and this goes on basically. So you see what's basically happening. If you look at these values, these are getting smaller and smaller. So these are getting smaller and smaller because every time it's going, the time is passing, the denominator is going up. You see the denominator value is going up. As the denominator goes up, the overall value is basically reducing. So this fraction is basically reducing. Okay, that
So,
means,
excuse me.
yeah, yeah,
Actually, I had a question. Actually, I want to
yes.
ask. Actually, the thing is that you've taken actually from first you are getting 160 volt. It should be. I think it should be calculated by using at load by using the KVL ZL by ZL plus
You're saying, okay, you're
Z0
saying the
in multiplied
V
160.
V1 plus will be something like 200 divided by 200 plus 50 into 160, right?
Yeah, yeah. Why have not calculated? Yeah. It
Yeah,
should
it
be like
should
this.
be 55455, 4 into 160 divided by 5, 160 into 4 by 5. How much is this? 0, 6 are
720.
24. How much it will come out to be? 5152. Is it 100? Yeah, it's 640 divided by 5. 5 to 10, 5840. So it'll be 128 volts, right? Yeah.
Yeah.
Yeah, it should be 128. That's a mistake. Yeah, I did here. So if it is 128 volts, yes, I skipped this particular step, which is basically important because at time V1 plus will be exactly equivalent to the distributed voltage. You're right. So this will be 120. This will thank you for this. This will be 128 volts, and this will be 128 divided by 3. But that doesn't change the basic thing which we are basically uh, seeing here, that overall the voltage as you go up in time, it's going to reduce in fraction. So instead of 160, it's basically 128 divided by 9. It's 128 divided by 27. This is 128 divided by 81, not 1. And as you go up, you see that these particular values are reducing. So it's sort of, if you are giving some voltage, let's say this is a voltage pulse, then as it gets reflected, the reflection amplitude is lower, then it gets lower, then it gets lower, lower, and lower. And finally, basically, the entire system stabilizes. That is the basic assumption of this. And now, what we were supposed to compute is uh, the voltage at the source and the load end at time t equals to 4.5 picosecond. Now we need to see how much is time 4.5 picoseconds. If this is if 1 TD is 1 microseconds, that means 4 TD will be around 4 microseconds. That means 4.5 microseconds will be around 4.5 times TD. So we need to see the voltage at the source and the drain end at 4.5 TD. So if this is force, this is 4.5 TD. So we need to compute basically this particular voltage. So at this particular time instant, which is 4.5 TD, we need to compute the voltage, which can be, so this is around, let's say, we can compute a range of voltage, let's say from between time t less than 5 TD to 4 TD. We can compute this particular voltage, and it's going to give us the approximate value of this particular voltage at this particular time instant. So how can we compute this particular voltage is summing these particular voltage at this particular time instant. How much is it? It's 100 and, let's say, 128. It'll be starting from, let's say, 128. Let's first of all draw the overall schematic, how it will represent the voltage at the load end as a function of time. This is time at time TD. This will rise to 128 volts, and then it's going to be 128 plus 128 divided by 3. How much is it? I don't know the value. It'll be obviously slightly increased. It'll be increased. Then it is minus 128 divided by 9. So it'll be slightly reduced. It'll be slightly reduced. So this is basically 3TD. No, I'm just, this is what 160, 128 divided by, so this is not, yeah, this is 128. So this is 3TD. This is at the load end. And now again, it will be how much? It will be minus 128 divided by 27. So how much will it be? It will be around, we need to compute it. 128 divided by 3. Whatever the value is, let's compute it later on. But this is the exact calculation that can be done to compute it at the load end. So it's 128 divided by 3. Okay, and 128 divided by 9. I guess we made a mistake here. Yeah. So this should not be like this. Pardon. Okay, so this will be 128, this thing, then plus 128 divided by, it'll be minus 128 divided by 9, which will be in 3TD, this particular thing. Then it'll be plus 128 divided by 81, this particular thing. That can be done. So it's initially going like this, and then it's slightly reducing, and then it's slightly increasing, and then whatever can happen. It's basically 3TD, then this is 5TD, then the next one will be 7TD, which is not of our concern. Okay, so we needed to find at the load end what will be the value at around. If this, then this will be 4TD. We needed to find the value at around 4.5TD, which will be exactly this value after you compute. This will be the value at 4.5 microseconds, whatever the value is. I don't want to solve the fraction right now, but this will be the exact value. And from the source end, if we draw the source end, the source and value, obviously the source and the voltage is going to start initially at 160 volt, and then it will be 160, then it will be plus 160 divided by, sorry, why am I writing 160? 128 plus 128 divided by 3, and then it will be minus, not minus, it will be 128, and it'll be 128 divided by 27, and that's it, up to 5TD. So it should look something like this, and or maybe we did a mistake because it cannot go above 160 value. That doesn't make sense. Why am I writing 160? This is 120. Initially, this is 120, but this is 160. Yes, this is 160 volts. Did we do a mistake here? So yeah, that makes sense. That makes sense. So if it was initially 160 volts, the next particular value is mm, it's going to get reduced by 160 minus 128 divided by 9 minus 128 divided by 27, and then yeah, this will be it. So it'll look something like, I guess should be plus, and yes, so this will be around, maybe if this is 0, this is 2TD, this thing is 4TD, this thing will be 6TD, which we don't care. Then we want to find the voltage around, this will be 5TD, We want to find the voltage at this point, which will be 4.5 TD. So this will be the exact 4.5 microsecond point, and you need to compute this particular value after solving the fraction. So that will be the exact answer of this. And yeah, you just need to care that you compute initially this particular value so that you use the exact value in the lattice diagram. So this is about this question. And I guess the answer should be around 191, and it should be either this or this. I guess it will be around this value. I don't know, you just need to you just need to solve the fraction so that you get the exact answer. And what one thing is, yeah, that is the point. Yes. If this is the, you see the initial, if the initial voltage is, let's say, 160 volts, then you see that at 4.5 microseconds, hmm, does it make sense for this voltage? Yeah, so at 4.5 microseconds, it's the source voltage becomes 191.6 volts, and at the load end it becomes 189.6 volts. Hmm. Okay, there is. I'll check this question and maybe I'll see if the values given are correct or not, because I don't know exactly. The procedure to solve the question is exactly same, but there is something missing in the question, or maybe there is some sort of a error in the question. Then we will get back to this question in the next session. Right now, you can even cross-check whether the values used are correct or not. But let me just see if we can. Mm, no, where was my sort of lectures? Yes. So in this particular scenario, if we compute the source voltage, which is voltage source, then it will be around. Hmm, how much was the initial voltage? In this case, it was 45 volts minus 5 volts plus 0.55 volts, and that's it. So this is the voltage at the source end. So this will be 40. This will be 40 plus 0.55 volt. This will be 40.55 volt. So in the example I showed, if we compute the voltage at the source as a function of time, then at time t equals to 0, it was initially 45 volts. Then it dropped by 5 volts. This is dropped by 5 volts. Then it stayed. This is 2 TD. Then this is 4 TD. Then it increased slightly and went up to 40.55 volts. So this value is 40 volts here. And then it stayed. So this makes sense. So that the overall value finally will be around, it'll be stabilized. So yeah, so this makes sense. And this also makes sense because the final value attained is, okay, goes down. I don't exactly know that if you are giving a source voltage of 45 volts, and if how the reflections will cause the voltage to go above 45 volts. I don't think that scenario can happen because it cannot go greater than sort of a value. That's why I'm looking basically that there is some sort of a error in this particular question. Hmm, did 180? Yeah, okay, let's get back to this question once we are done with it. But this is the exact procedure of solving these particular problems. Maybe there might be some mistake with the calculation done. And what if we can take a question from this week? No, this is not related to it. So first, let's clear what has been basically taught. Then we can get back to it. Now, if we talk about, let's say, what happens if you now have a, let's say for example, an AC source in a circuit instead of a DC source. And we are considering the simplistic AC source instead of let's say a sinusoidal source, which is not difficult to deal with, but we'll just consider a source which is sort of turned on at time t equals to zero, and it's basically closed at some time t instant t. So you have a voltage source as a function of time. So it will be sort of a step like at time t equals to zero, it's turned on, and that means the circuit is closed and it stays up to time t. So this is sort of a pulse. And let's say, let's assume that this time period, which is time period t, is approximately 10 times td, which has been basically discussed in the notes. So that means it's 10 times the delay time in the transmission line. Okay, so now how will you draw the lattice diagram for it? Let's for example, and also assume that the reflection coefficient from the source end is basically plus 1 by 2, and the reflection coefficient from the load end is also 1 by 2. Okay, now what's going to happen when you draw the lattice diagram for this, where this is t over td, this is z, this is equals to 0, this is equals to L. That means you have now a time varying source with the some source impedance. This is the load impedance, and this is V1 plus, which you compute obviously from Z0 divided by Z0 plus Zs into the source voltage. Now what's going to happen? So initially you have, let's say, time td t1, 2, 3, 4, 5, 6, 7, so on and so forth. And this particular thing is 10 times td. Okay, so 10 times td, if you draw it on a time scale, it's going to look something like this. Because 10 times td will be somewhere here. This is 7 td, this will be 8, 9, 10, so it'll be around up to this point. So this will be 10 td. Okay, maybe we can draw it more better way, something like, so this will be, okay, t over td. So this will be 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. We're shrinking sort of. So this is the exact unit step pulse which is basically being given to the system. So this is t equals to td. T equals to td. 10 times td. This is the time period of the pulse. And now you have one more of this particular axis here. So this is z equals to 0, z equals to L. So initially, this is point TD. Okay, so initially the voltage will rise, as you know, governed by V1 plus. So this will be V1 plus, which you can compute simply from this particular thing. Okay, now after 1 TD, you know that the voltage is going to get reflected. How much it will be? It will be this V1 plus uh, divided by this particular coefficient. And this is basically V1 plus into the reflection coefficient. Okay, and then again it will be reflected at towards the load at time 3 td. Again it will be, the value will be V1 plus divided by 4. So again it will be reflected. It will be V1 plus divided by 8. It will be again reflected, so on and so forth. So that's going to happen. And but the point is that how will the basic voltage look like towards the load end? That is the fundamental thing which we want to see. So voltage at the load end as a function of time. Up to time td, there will be no voltage. Okay, because this is the delay time to reach the load end. At time td, it's going to rise and reach this particular value, which is V1 plus. And now it'll stay at this particular value. And now after time 3 td, it's again coming back to the load. This value will be, it depends upon whatever the value is. It can go on increasing, it can go on decreasing. It can be, let's say, V1 plus divided by 4, and then it will stay like this, and then this, then this. It depends upon how much values are basically given in the calculations. Depends upon basically the reflection coefficient and transmission coefficient. So here the reflection coefficient and transmission coefficients are being taken like this. But if the reflection coefficient and from the source and then the reflection coefficient from the load end are different, then accordingly these particular steps are going to vary. It can also look something like maybe this. It will go up, it can go down, it can go something like this. It depends upon the reflection coefficient, just like we computed in the previous example. And now, now what's going to happen? This is basically going to happen because you see that actually you were giving a voltage like this, which was 10 times TD, step volt. This is a function of T. At the load end, what you will basically see is something like this. It will go on increasing and then it will go on reducing. And this will be around 20 TD. Okay, so this is the function of time. So this will be at the towards the load end. Finally, because after the time it takes 2 TD to for the voltage source to reach back to this source end, and then it takes again time 3 TD to come back uh, to the load end. So the overall time will be increased once it is going to reach the basically the source end. So now, and how will the exact scenario look like? It will look like if you're giving a voltage Vs of t at time t equals to 0, and this is exactly 10 TD, then towards the source it's going to be at time t equals to 0, then it'll come back, and then it'll come back, and then it'll be something like this. I mean, the reflections, there will be reflections of this pulse, but once the reflections will happen, the basic assumption is that overall thing will finally stabilize. This is not exactly voltage source, but this is exactly how these pulses will, the reflection of the pulses will diminish in time, the reflection of the pulses. And that is, I guess, in the first week itself, I showed you that once you give, let's say, even a sine pulse towards the load end, the reflected pulse will be diminished. Okay, and then it will again go back to the load, and it will be again diminished. It will come back, it will be again diminished. It will go back to the load, it will be diminished, and then so on and so forth, and finally it will stabilize. That is basically the concept of these particular reflections, because what governs the amplitude of this reflection, how much of this particular pulse is basically reflected, what governs it is basically the reflection coefficients. Let's say if the reflection coefficient from the load end is 1, it means basically the same amplitude is reflected. Okay, so if the reflection coefficient is, if the reflection coefficient is 1, the same amplitude will be reflected. And if the reflection coefficient is around zero point 0.5, that means around half of the wave is basically reflected. But it also depends upon the resistance values. So the resistance values are important. Okay, the resistance values are important. And but essentially this particular reflection coefficient that determines how much of the amplitude is basically getting reflected. And one more important thing about these reflection coefficient, it is sign. So when you see that there is a, let's say, reflection coefficient of, it can be -1, the reflection coefficient can be +1. Okay, what does this sign mean? It basically indicates the phase of this particular thing. Whenever for example, you are given a pulse like this that goes towards the load, and if somehow the reflection coefficient is -1, somehow by some scenario, it can happen by multiple causes. What basically this indicates, it basically indicates the phase flip of this particular wave. Uh, I don't know why. Hello. Was it stuck? So it indicates basically that something which is reflected will be flipped in phase. So it will look something like this. But it can be with the same amplitude because it's 1. But you know that reflection coefficient value is, it is less than 1, greater than or equivalent to 0. This is the range of the reflection coefficient. But the sign here indicates basically the phase flip. Uh, it sort of changes its phase completely. So this can indicate a 180 degree phase shift. 180 degree phase shift. Okay, and you can compute it using simple mathematical analysis. It's not a big deal. That means, let's say, for example, let's talk of a mirror. If you have a mirror, this is, for example, a mirror, then you have a electromagnetic wave coming in towards the mirror. Now, basically, there is a reflection of the electromagnetic wave, and you know that once the electromagnetic wave comes like this, and it doesn't go back exactly like this. There's a phase shift of 180 degree because of the impedance mismatch, because it was traveling in medium with refractive index n1 and the mirror refractive index is n2. So the reflection coefficient is basically going to determine that the reflection coefficient here will be n1 minus n2 divided by n1 plus n2, which is basically air refractive index minus glass refractive index divided by their summation. And you know that the refractive index of glass is greater than, let's say, air, then if N2 is greater than N1, then the refractive index will be not the refractive index, the reflection coefficient will be negative, and this negative will act as a sort of a in the phase itself. So the reflected wave will something look like this. That means the crust where it was earlier, it's going to be a trough now. So the crust and troughs will be opposite to each other. So this is basically a 180-degree flip of the waves. So that's exactly what happens in these particular cases. But I don't know if that has been talked about, if the phase flips have been talked about. But this is exactly what happens in circuits also. And these phase flips are essential even in if you are dealing with electronic devices, if you are dealing with optics, these have to be essentially taken care of. Even in let's say, for example, mm, even if you are dealing with electronic devices, these and if you are treating electrons as a wave, then these phase flips also occur there with the electrons wave. Let's not go into that detail. Now, what we are going to do is we are going to consider the time domain. This is basically the time dependent, or let's call it time domain analysis of the transmission lines. Okay. Now, what's basically happening is you you might have seen that if there is sort of a single IC, two ICs are connected with each other, which are basically some performing some logic operations in a circuit. So this is sort of a performing some logic operations in a circuit, and these are connected by certain traces, which are basically the transmission lines. Okay, and essentially what is basically happening is that these transmission lines are fed to certain IC. So this is sort of a IC. It can be a logic gate. And what is logic gate composed of? It's composed of transistors. And transistors means that you have a sort of a, let's say, NPN transistor connected to another transistor. Just like I showed you in the previous weeks, that if you connect a, let's say, a PNP transistor to an NPN transistor, and you just tie the gates around and just ground this. This is some constant. This is some constant DC voltage, and here you apply some sort of a time varying signal. If you apply one at the load end, if you compute the load at this particular volt output, you're going to get a zero. So you're going to get a 0 volt. So this exactly acts like a NOT gate. This exactly acts like a NOT gate. So you give one, you get zero, you give zero, you get one. So this is exactly how it happens. But the essential thing is that the response is not exactly abrupt. You don't get the abrupt response. Let's say for example you give certain voltage, let's say, and this 1 and 0 is nothing, is certain voltage level 5 volt. Okay, so and this 0 is, now you will say what is this 0 volt? You cannot measure 0 volt, but the 0 is actually some threshold voltage. If it goes some below some threshold voltage, then that is basically read as 0. So it looks something like this. Okay, if this is 5 volt and this is some threshold voltage, if the voltage goes below this threshold voltage, entire region is treated as zero, which is basically digital zero. Otherwise, it doesn't make sense if you are having zero voltage. Whenever there is binary zero, there is some voltage there. Otherwise, it will not be able to read, but that voltage is less than the threshold voltage. If the voltage is greater than threshold voltage, it will be treated as 1. and below this it will be treated as 0. So that is a simple scenario of the digital circuits. Now, what happens basically when you compute the output at the load end, there is basically the load resistance, then there is a load capacitance which comes into picture. Okay, this is the load resistance, this is the load capacitance. Why does it come into picture? Because it comes from the inherent nature of the transistor. You know, a transistor looks something like this. If you talk about a BJT even, this is a source, this is a drain, this is the, oh God, what happened? This exited, I don't know why. Oh, this got disconnected, sorry, because of some issue. I'm not able to join back. What's happening? This Windows. It's not good. Why is this internet connection not stable? It's not working.
The internet is not working? Ah.
I got disconnected in the middle.
Oh, you disconnected, then you connect. Yeah, maybe to. Yeah, you need to.
No, not. I mean, I was in a meeting and I got disconnected, and now I'm not able to.
Ah. So did you switch it off and turn it on?
Yeah,
Okay, fine. Maybe to.
maybe. It will work.
So yeah.
Hello. Uh, Sorry for the interruption. There was some issue with the network. I don't know how it happened. Let's try to share the screen again. Okay, so it should be visible now. It's recording as well. Okay, so what I was saying is that these particular I was talking about that these capacitances and the resistances they arise because of the structure of the transistor, how basically a transistor is made. So this is a metal, which is a metallic gate. So this is source terminal, this is drain terminal. And you know that because of the because of let's say these overlap regions between the gate and the drain, the source and the gate, there is sort of a capacitive effect between these two terminals. Okay, because at the end these are sort of this is a highly doped region, so this is a metal. So these are like two plates of a capacitor. In between them there is a dielectric. These acts like these give rise to a capacitive like effects. There are also other resistances, sort of 5 to 6 resistances. Let's say this is CGS, this is CGD, which is the gate to drain capacitance. There's also metal to body capacitance, and all sorts of capacitances are there. So they give rise to these sort of capacitances at the output. And they also have resistance because resistance is sort of an intrinsic whenever the electrons flow inside certain system. Okay, and this give rise to this particular RC network at the output end. And once this RC network is basically there, it gives rise to a time constant, which is basically R times C. So this time constant is basically another delay time, which is basically uh, which is basically seen at the output. That means if you, let's say, for example, give uh, for example, maybe a step voltage like this, which at the source end, at the drain end or at the output end, basically how the voltage is going to rise. Maybe it's not going to rise like this. It's instead going to rise somewhat like this, and then it's going to drop. That means there will be this rise time and then there will be this fall time. And this rise time and fall time is basically controlled by this RC time delay, which is basically this resistance value and the capacitance value. Usually this capacitance value is very small. It's of the order of can be picofarads or can be maybe nanofarads. This is very small value of the capacitance. But even though it gives rise to a time constant of maybe of the order of nanoseconds, or even if it's a picosecond time constant, most of the time it's in the order of nanosecond, that's going to cause a significant delay in the signal. Okay, so that is the fundamental thing about it. Now, as you have been as we have been talking about what is basically happening, now you have a sort of a load which is basically connected to a capacitor. So you have sort of a XC type, which is basically a reactance. Instead of a normal resistance, you have a reactance. It can be capacitive, it can be as well inductive, depending upon the circuit system. But it's not inductive here, it's capacitive most of the times. So this capacitive reactance is basically 1 over j omega c. That means for omega tending to 0, you have XC tending to infinity. That means this it's not going to allow the DC to pass through it. That's just the fundamental property of a capacitor. Once you have the DC source applying to the capacitor, it's not going to allow the uh, current to pass through it. The impedance or the reactance becomes infinite. But when the AC is applied to it, it starts the charging and discharging processes. Okay, so that's the fundamental properties of the capacitor you might have seen in the network analysis course. I am not going to go back to this course again, but what we are going to see here is certain things which are necessary to basically analyze these particular circuits. So now, if you for example have a if you for example now have a source, a voltage source which is connected to, let's say, a resistance, and then you have a transmission line connected to it, and it's ended at a load which is sort of a capacitive in nature. Sort of ended with a load which is capacitive in nature, and this is the voltage across the capacitor. Okay, you know that any voltage given to it will rise with certain time constant, uh, which is given by the RC time constant. That's what I was basically discussing in the case of a transistor, because there will be intrinsic resistance associated with it. So this will be R, this will be C. So this is going to determine the rise time of the voltage. Note that this is not the delay time associated with the transmission line. So this time delay is different. So this is the time delay which is equivalent to the length of transmission line divided by phase velocity of the wave moving through the transmission line. This time delay is different. It depends upon the RC value. It is basically intrinsic to the load. So this is intrinsic to the load. And it adds on a time delay over the time delay caused by the transmission line. Okay, so this is the separate time delay. It's not the same time delay we are talking about. And now, if we, for example, have, let's say, a sort of a network, something like this, then we can simply apply KVL, KCL. We simply apply KVL or KCL in order to analyze basically the voltage and the currents. And you know that the current across the capacitor can be given by dVc divided by dt, which is basically the current across the capacitor. If it would have been an inductor, you could have write the voltage across the inductor is basically dIL over dt, which is basically the rate of change of current through the inductor. But here we are talking about a capacitive load. So once we have this particular thing, write a we can write a KVL across the loop, and it can give you exactly what is basically the uh, V1. If we need to find, let's say, V1 plus, we need to find, uh, just like in a lattice diagram, if we talk about the voltage, initial voltage at time t equals to 0 is basically V1 plus. It gets reflected, reaches towards the source end, then you get a voltage of V2 minus, and again it goes back and forth in the circuit because of the impedances. Okay, this load is also going to act like an impedance. But the difference here is that this impedance will now be, or whatever the, I should say, reflections of this particular wave, it will be sort of a now time dependent. Why? Because because these quantities are time dependent now. So these are sort of a voltage across the capacitance, or current across the inductance. So these are sort of a time dependent things. Why? Because that's what I talked about. If you have a capacitor, or if you have even an inductor, then there'll be certain basically time associated with, let's say, let's say the rise time or the fall time associated with the capacitance. Even something called as, if you have a capacitor, you give it certain AC voltage, this capacitor is going to charge, and there will be certain charging time associated with it. This charging time is also going to determine, this is basically a time dependent thing. Okay, it's going to charge up to a certain time. Let's say it charges something like this and reach the maximum value. So this particular time constant will be there, and this time constant will be reflected in the this time constant will be seen in the reflected wave towards the source end. So that's why this entire phenomena becomes time dependent. You didn't have any sort of a time constant if this there was only a load which was resistive. But if there is a capacitive load or an inductive load, because of the voltage and the current nature across the because of the voltage across the capacitor, this is sort of a time dependent thing, because the current across it is time dependent. It charges and it discharges depending upon the certain time constants. So that's going to get reflected in the reflected wave, which is going back to the source. So the entire thing now becomes time dependent. And now for that, you basically need to solve the simple KVL equations, but by considering these capacitive natures of the, I should say, the loads. Let's say if you write a KVL for this circuit in a simpler terminology, you can write it something like V1 plus, which is the voltage at time t equals to 0, time t equals to, no, why am I writing 0? TD, the voltage reaches the capacitor, and then there is VR as a function of t, which is equivalent to VC of t. That means the overall capacitor voltage, which is basically this. And if you have, let's say, for example, if you write this as, in terms of the voltage across the capacitor, you can write, or you can even, for example, write in terms of the currents, because the current across the capacitor is C dVC divided by dt. So you can apply the KCL even, and you can write basically V1 plus divided by Z naught minus VR of t divided by Z naught, which is basically the current, which is equivalent to VC dVC divided by dt. So you can write it as V1 plus minus V1 of t, which is equivalent to Z naught C dVC divided by dt. And simplifying this equation is basically you're going to solve it for as a VC. So you basically want to compute VC as a function of t. How you're going to obtain it? You can basically write it in terms of, you can basically take out the terms and write it in terms of VC as a function of t. You can maybe write it in terms of V1 plus minus V1 of t divided by Z naught C, and this is dVC by dt. So you can write VC of t, dVC will be equivalent to integral V1 plus minus V1 of t divided by Z naught of C into dt from some time t1 to t2. So this is the exact thing you can solve, or you can even solve a differential equation, which will be something like uh, something like V1 plus which is equal to Z naught C dVc divided by dt plus Vc of t. If you solve such sort of a differential equation, the solution of this the solution will be exactly of the odd type e to the power minus t by tau, where this tau is basically z naught times c. So this is sort of a time constant I was talking about. So this is a resistance times some sort of a capacitance, and you can obtain the solution of this particular differential equation, something like v1 plus 1 minus e to the power minus t minus td divided by tau into u of t minus td. So why this t minus td is basically there? It doesn't come, it comes from the natural thing that there is a delay of the source voltage. Once it reaches the capacitor, there is this sort of a time delay. So it reaches the capacitor after a time delay of td. So that's why the shift in the time has to be seen in the equations. Okay, this time td is representing basically the time delay associated with the wave motion. Which wave? The voltage wave, which we are basically applying at the source. So that's why there is td. So that's why if you see that I'm at time t equals to td, this will be 1 minus e to the power 0. This will be what will it be? It'll be 1 minus 1, so it'll be v1 plus, so it will be ut minus td. So this will be Vc of t will be equivalent to 0. That means it's basically started to charge, and after a certain time the voltage will reach its maximum value in the capacitor. That means at this particular time it will be fully charged, and once it's fully charged, the circuit's output circuit will open, and then again when it will when it will sort of discharge, it will again start to charge, the circuit will close until it's charged, it will again start to open the circuit. So that's how the transient of the capacitor basically works. And now what is basically happening is, that is the fundamental thing, the charging of a capacitor. If you have the voltage across the capacitor or the load, it's going to increase somewhat, something like this, and it's going to reach the steady state value at time t tends to infinity. And this particular time constant is z naught times c. This z naught can be a simple resistor. So this is basically the time constant associated with it. Okay, now how it's going to look like in sort of a if you talk about uh, let's say for example, if you have a now if you want to write Vr as a function of t, how it is going to look like, it will be at time td there will be sort of a negative spike, and then it will sort of go towards this particular v1 value. Okay, so this particular negative spike is basically minus v1 plus, and this negative spike is basically implying that there is sort of a phase shift, in the voltage signal. That's what exactly I was talking about, that if you send a voltage pulse like this and your reflection coefficient somehow is negative, then you are going to get a voltage pulse like this back. That is exactly the same thing that happens with a mirror I talked about. If you have electromagnetic wave like this hitting a mirror, it will go back like this. That means there is a phase shift. This is phase shift of pi, which is basically 180-degree, because of the reflection coefficient is negative. That is the same thing that is happening here. This particular pulse is basically becoming negative because of the reflection coefficient being negative. Once you have sort of a capacitive or an inductive load, the reflection coefficient, if it becomes negative, then there is a phase shift of the reflected pulse. Okay, now again, this particular behavior, if it happens with the capacitor, you can do the similar analysis, and if you see that if you draw the Vr of t as a function of time for an inductor, you will get a pulse like this, a peak pulse like this, which is basically a spike. Okay, and what is exactly this thing is that if you have a transmission line, and if this is the input side, this is the output side of a transmission line, and there is some sort of a load. Let's say this is a capacitive load, and you are measuring using a TDR scope, which is basically a time dependent sort of a reading of the reflected voltage values. If you are reading a voltage something like this, and if you are reading a voltage something like this, that is going to give you a indication that what sort of a load is present at the at this particular terminal. That means whenever if there is some sort of a cut in the transmission line or the transmission line is not proper, you are going to get its indication by using this particular scope at the input end. And it's going to give you the information about whether the load is inductive, whether the load is capacitive by looking at these particular voltage spikes. That is the important thing about basically these TDR scopes and doing the measurements at these particular input terminals to read the reflected voltage. Okay, and you don't need to measure exactly at these particular capacitive ends in order to understand what is basically the load. You can basically just why am I connecting it to the same terminal? This is not good. So it should be here. So basically what is going to happen is that you're going to get the information about the load by measuring it at the source terminal itself. Now, now what is basically going to happen is sometimes if you give a pulsed pulsed form of a wave, let's say this is a voltage, and this voltage is sort of in pulsed form. Uh, Most of the time it's given in sort of a digital circuits. How is it going to behave is basically, again, it depends upon what sort of a load is there. If it is a resistive load, whether it's a capacitive load or an inductive load. The pulses can, if you give sort of a pulses to this particular circuit, and let's, for example, assume a scenario, if this is a pulse train given to a circuit, and this time is basically, let's say, T1, which is basically the time period of the pulses. And you have a capacitor at the load end with a time constant of, let's say, RC. And let's say this time constant is much greater than T1. This is greater than T1, which is the time period. What is exactly going to happen? That as soon as this first pulse comes, okay, it starts to charge the capacitor. And before before the capacitor before the capacitor reaches to its maximum value, another pulse is coming in that particular same time instant, and it's the capacitor is not going to behave exactly as it was supposed to behave. That means the charging was supposed to like happen like this. Now the charging will happen something like this because of these pulses coming in at certain time instants. Because this charging time was tau equals to RC is greater than T1. So that means it's going to take longer for this capacitor to charge, but before it will fully charge, the another pulse is coming, then another pulse is coming. So the capacitor, if the effective capacitor is or the voltage across the capacitor is going to behave something like this. So it's going to be sort of a bumpy. Okay, and it depends upon if it's even an inductive load, then again it's going to behave something like that. If it's a capacitive load, the discharging is also going to be determined whether you are controlling this particular time delay or the time period of these pulses effectively. Okay, so these are essential quantities in a circuit whenever you're dealing with the time circuits, or even in, let's say, what's that called? Even in clocks. The clock is basically sort of a circuit that basically synchronizes the I should say voltage waveforms or the current waveforms in all of the circuits. And it's usually in sort of a megahertz, it can be in gigahertz. That means if it's in gigahertz, that means you're giving the clock in at a nanosecond time delay. That means that it looks something like this. It's not exactly square, it's almost of this type. That means this particular time period is around nanoseconds. That means it's a gigahertz clock. And if it's sort of having a time period of the nanoseconds, that means the capacitor it is connected to, that means the load capacitor should have a time constant which is less than this T1 so that it should charge and then it should properly act in a circuit. Otherwise, there will be sort of issues that there will be charging bumps in the capacitor, which is detrimental and it's not usually required unless and until there is no specific usage of the circuit. This is sort of a basic example, a layman example, which I'm discussing here. The other cases, which are basically realistic scenarios, are more complicated in terms of how the clock is basically used to control the circuit based upon how much the time delay is associated with the capacitor. Now, if we, let's say, for example, check the questions simply that how it's basically going to behave, then let's for example see if you have a capacitive network, if you have a network, a lossless transmission line that has a low termination of a series of inductance shunt capacitance. So you have a termination something like this, which is basically a inductance and a capacitance. So this is sort of a this is sort of intrinsic impedance of the transmission line, and the what is the thing that is given. So there's this TP, which is basically the time delay associated with the transmission line. They have changed the terminology. I don't know why. We usually write it as TD, and we need to find which is the correct input, which is the correct TDR measurement at the input terminal of the transmission line. That means you have the source, you have some sort of intrinsic impedance of the transmission line, and you have the transmission line, and it's connected uh, to inductance and the capacitance load. And this is the voltage at the source, this is the inductance, this is the capacitance, this is having some intrinsic impedance Z naught, and there is a time associated with this which is basically tau TP. That means which of the following is correct about these particular about the transmission line. So these are sort of scenarios which is basically shown that how a particular waveform will be basically I should say uh, what should I say? It's connected to a voltage source which is switched on at time t equals to 0. Okay, so it's a voltage source. It's closed at time t equals to 0. It's sort of a it's sort of like this. At time t equals to 0, the voltage source is closed, and then it will remain up to some time. Or if it's not, if it's staying constant up to a certain time. Okay, so it's sort of a step-like response, unit step function of t. And this it goes up to, I don't know, it can go up to infinity. So it's staying like this. Now what's basically happening is we talked about that if this is an inductance and then there is a capacitance. We talked about that the reflected wave will look something like this. There will be a spike because of inductance, and because of the capacitance there will be a down spike, and then it will go on. So that is the exact answer of this question, which we basically checked here. Because of this particular here, we had only a capacitive load, because of which this negative spike came. And now if you have an inductive load, you will get a spike like this, and it will go on. But now we have both R and C present here. And because it's encountering the inductance first, the reflected voltage, which is going to start after certain time, okay, it is going to have the inductance peak, and it's going to have a capacitance peak, down peak, and then the voltage will remain the same. That's exactly what is shown. The voltage is zero. That's the voltage is zero, let's say, and it's going to rise. Then there will be this inductance peak, then there will be this capacitance minus peak, and then it will stay constant. So this is because of inductance, this is because of capacitance, and then there will be this 2 time delay associated with the voltage waveform, because you are measuring at the input terminal. So at the input terminal, once you are turned on, it will go through the circuit, take time TP, then it will come back, take time TP. So this will be overall 2 TP. So that is what basically this 2 TP is representing. And because of inductance, there will be a positive peak in the voltage. Because of capacitance, there will be this negative peak. And you can just see it from the equations even. That's the answer of this question. I guess this should be the answer. And now, if you have a lossless transmission line with a characteristic impedance R0 terminated at Z equals with an inductance L, so you have a transmission line with the inductance L. Let's not draw it like this. Let's draw it like this. And a DC voltage is applied at t equals to 0. So you have a DC voltage applied at t equals to 0. That is same as this, applying at t equals to 0, a voltage unit step function. This is basically a DC source right here because it's going on up to some certain time. to the line at z equals to 0. So this is equals to 0 point, this is equals to L point. This is inductance L, this is small l, which is the length of this. Through a series resistance R naught. It has a series resistance R naught, the amplitude of the reflected wave measured at the input terminal. The amplitude of the reflected wave measured at the input terminal. Okay, so we need to measure the amplitude of the reflected wave, which is VR of t at the input terminal. That means at these particular terminals. So if you connect a scope at this particular terminal, you need to find VR of t. Okay, how you are going to find it is basically, let's say for example, you have a, let me just add a page here, add a page. Let's say you have a voltage source, which is a DC source. It's connected to some resistance R naught, and let's say you have an inductance load, which is L. Then let's assume this is V naught. Then there should be some current flowing, let's say I load current, and then this is the voltage across the inductor, which is VL. So what is basically going to happen is this. Let's call this as Z equals to 0 point. This is Z equals to L point. Okay. There is also another capacitor in resistance, which is basically R naught, which is basically the characteristic impedance of the transmission line. Okay, this is the impedance of the source end, but the values are given as same. They are both given as R naught. Okay, so accordingly, when the voltage will come at this particular end, it will basically the voltage will sort of get reflected from the inductance and it will reach back. So what we are supposed to measure is this particular voltage as a function of time. Okay, so what we can do is that we can write simple equations in terms of because for the inductor you know that the voltage across the inductor is L dIL divided by dt. So you can pretty much write maybe it you can write a KVL or you can write a KCL, whatever you like at this particular node. But it's better to go with the, let's say if we write in terms of the voltage, then the current across the inductor will be something like, there'll be distributive network. So initially there will be V1 plus voltage. Okay, so V1 plus divided by R naught minus V1 minus as a function of T divided by R naught, which is basically the reflected voltage going in this direction. This is V1 minus as a function of T. This is V1 plus. Okay, and because the voltage across the voltage across the inductor can also be written as in terms of L dIL divided by dt, and you can also write the voltage across this particular terminal in terms of V1 plus and V1 minus. What you can basically do is that you can compute the V1 plus as, let's write it as VL of t. You can write it in terms of, so for, let's say for example at z equals to L, and for we are considering time t greater or equivalent to the some sort of a time associated with traveling the wave. Once, let's say the wave takes time period t to reach the load end. So for time greater than t, what we are going to see is that there will be uh, I should say a voltage across the inductor that will be V1 plus minus V1 minus of t. Now this is plus. And we now have, for example, we have, this is equation 1, we have equation 2, we have equation 3. So what we are supposed to compute is basically uh, we are supposed to compute V1 minus of t, because that will be the voltage waveform that will be reflected towards the load end. So now how we are going to solve it, if we take, let's say we take this particular equation, equation 3, and we take this particular equation, which is equation 1, let's say from equation 1 and 3, we can get this is V1 plus, V1 minus, this is V1 plus, V1 minus. So once we solve it, we get VL as a function of t will be 2V1 plus minus R naught IL of as a function of t. Let's call this equation 4. And now again from equation 3, which is uh, again from let's say equation 2 and equation 2 and equation 4, we have VL on the same side. We can write basically L DIL divided by dt plus R naught times IL of t, which is equal to 2V1 plus. Okay, so let's call this equation 5. So this particular equation can be solved, and the solution in terms of whatever you need, whatever is here, let's say this is, so this is a differential equation in terms of IL. Okay, this is a differential equation, sort of something like if you write d by dt as an operator, a differential operator, you can write as something like L differential operator, L differential operator plus, if you take it as common, let's take this as common, DIL, let's assume d by dt as an operator, then this will be plus R naught IL of t, which is be 2V1 plus. If we write it as LD plus R naught IL of t, which is equal to 2V1 plus. So you can solve this particular differential equation, and you know that the solution, you can basically, what you can do, you can simply divide by, R naught, you will get maybe, or even you can divide by L. That's just your own choice. But anyways, you are going to arrive at a solution which will look at IL of t, which is equivalent to 2V1 plus divided by R naught, 1 minus e to the power minus t minus t R naught divided by L into, there's no multiplication. It can be unit step, but it doesn't matter. So this is the exact solution of this particular differential equation. Why does t? The because of the time delay of the transmission line. So the time origin shifts to t. So that's why you write t minus t, where this is exactly the length of the transmission line divided by the velocity of the wave, phase velocity. So this is exactly the current across this inductor. Now let's call it, for example, equation 6. And what happens is basically, now if we write the current across the inductor at time t equals to infinity, if you put this as infinity, you get twice V1 plus divided by R naught. Okay. And now if you want to find the voltage across the inductive load, you can find it by LdIL divided by dt. You can basically differentiate this IL. What you get, when you differentiate it, you get 2V1 plus divided by R naught into, I guess the R naught and R naught will go because R naught will come down. So this R naught will go into e to the power minus t R naught divided by L. And let's call it equation 7. So if you use this equation 7 into this particular equation, uh, which is equation 3. So using equation 7 into equation 3, what you're going to get is the value of V1. That means V1 minus of t will be equivalent to 2V1 plus into e to the power minus t divided by R into R naught divided by L minus half. This is L, and this is the voltage which will be basically reflected towards the where it is, towards this particular terminal, and that is what will be read. So the exact answer is basically twice V1 plus e to the power minus t. So it's exactly e to the power minus t R naught divided by L minus 1 by 2 twice V1 plus. And this particular e to the power minus t divided by L over R. This is basically the time constant of an inductor, L by R. For a capacitor, it's R times C, but for an inductor, it's L by R. So you can write it as tau. So this is the time constant associated with the inductor. Okay. The sort of So the sort of field, the magnetic field to develop inside the inductor instead of the, I should say, just like the charging and discharging of a capacitor. So this time constant depends upon the inductance value and the resistance value, and it'll give a similar effect in terms of the, I should say, the voltage of an inductor, which is L di by dt. So there will be a lag associated with the voltage and the currents. So that means if you give a voltage pulse like this, you will get something like this, okay, which will be basically a lag, a rise time and the fall time always associated because of this inductive effect, because there is a rise time and fall time associated with the developing of the magnetic field across the inductor, sort of similar to that of a charging and discharging of a capacitor. For the capacitor, basically the electrostatic field is there. So there's the electrostatic field because of positive and negative plates. But for an inductor, it's sort of a magnetic field developed. Okay, these are the magnetic field lines emanating from an inductor because of the current flow across the inductor. So that's the essential thing in this particular question. Now, this question 3 is again the simplest one, which I have discussed in the slides. That if you have a lossless transmission line with an inductive load, what sort of a measurement are you going to, what sort of a value are you going to note on a TDR scope at the input terminals? I told you that it will give a positive spike at the TDR scope. That is basically this. That means if you are giving an input something like this, what you are going to, this is input voltage. What you are going to get back as a reflected voltage will look something like this. This will be delayed with certain time, and it'll be like this, and then there will be a spike, and then it'll go on. Okay, it will sort of be spiked at this particular end. If would have been a capacitor, then the reflected voltage would have looked something like uh, something like something like this, a negative spike, a negative spike. Okay, so this is basically it comes from the previous analysis we did. And now, again, as these are simplistic questions, basically these are 10 plus 2 level questions now from the electromagnetic wave analysis, or even you might have studied it in basic electromagnetic wave courses in your bachelor's during the initial semesters of the bachelor's. So the Helmholtz equation is basically the sort of a similar to that of a wave equation, which you might have encountered, which where there is sort of a space varying component on one side, and then there is a time varying component on other side, and they are related by certain speed, which is the speed of the wave. Okay, so if you solve this particular wave equation in terms of the divergences and the curls, you arrive at an equation which is basically this particular equation, and that's called as Helmholtz equation. I don't know whether I have shown the derivation of it, but it's quite simple. You just have to start with the Maxwell's equation. So if you can see that how you write basically the Maxwell's equation, you can arrive at those particular equations. Just like you have del cross E, which is basically minus the time varying the time varying magnetic is equivalent to the time varying magnetic field, and you know that the magnetic field is exactly equal to mu times magnetic field intensity. Similar to the electric flux density is basically, or this is something sometimes called as electric, I should say, displacement vector is exactly equivalent to epsilon naught times E. That means this is basically how you can basically understand this sort of a, if this is sort of a material and you are giving in sort of a field which is as input and you are getting some output value. This is output. You are giving some field B field and you are getting output as H field, and or let's say you are giving in some input and you are getting some output. Then basically this output is some material response times the input, and this material response is basically all summed up in this particular mu naught and E naught. That's as simple as that. Okay, that is why there's a difference between the B value and the H value, and it's called as magnetic flux intensity or magnetic field strength, depending upon what you are basically measuring, and depending upon the material also, because this particular quantity, which is the electric displacement vector, it can also be something like epsilon naught E plus the polarization, which depends upon susceptibility times the electric field. So if there is a polarization inside the atoms of the material, it also gives another response which is basically summed up in the polarization. Now, how do you arrive at the Helmholtz equation is basically you take this equation here and you write it in terms of mu naught dou H over dou T, and then you basically curl both sides, sort of a mathematical trick people do. So you arrive at mu naught curl of dou H over dou T. So the curl will basically go inside. So it'll be mu naught dou by dou T of del cross H. And if you write it as mu naught dou by dou T of, so you can write del cross H from the Maxwell's equation is basically J plus dou dt divided by d. This is basically a displacement vector, and this is overall the displacement current density as a variation of displacement current. And you can write it as J plus dou dt divided by t. You can simplify it and you get exactly del cross E. It's equivalent to mu naught epsilon r dou square E divided by dou t square. So this is the exact equation we are talking about. Then you have to use certain identities here, which are basically the vector identities, so that you can write the gradient of the divergence minus the del square E, which is basically the Laplacian, is equivalent to certain quantity, and this particular thing basically the del dot E is equivalent to 0. That can be used here in order to, this is del cross E. This can be used to arrive at this particular, you will get minus del cross E is equivalent to mu naught epsilon r dou square E by dou t square. So this is exactly the Helmholtz equation which we are talking about. So you have a space varying term, you have a time varying term, and you have another term which represents the basically the speed of this particular wave. So it's almost like a wave equation. Just like I told you in a simplistic term, there's a space term, there's a time term, and then there is a speed of the wave. That is basically what this equation is representing. And if you just simplify it, bring the terms here and there, you arrive at this particular equation, which is called as Helmholtz equation, where this k naught is basically the something called as wave vector, and you know that E naught is can be written in terms of a phasor quantity with certain real component with certain magnitude, and e to the power j theta with certain complex term can be written in terms of a phasor. And what is basically important here is the thing that once you do this derivation, which is quite simple, anybody can do it, and it takes maybe a couple of minutes to do this particular set of derivation. The essential thing is when you write, if I take this particular first line where I wrote del cross E is equivalent to mine is equivalent to, actually it was del cross mu naught dou H by dou T. Okay, so we applied del operator, that means we applied curl on the both sides to this equation. Del cross E is equivalent to mu naught dou H by dou T. So from this equation, we went to this equation. But the essential assumption here is that this particular mu naught is not varying in space. That that is only when you can take it out of curl. Otherwise, it's not possible. That is why the essential assumption here is that this medium is isotropic. It is sort of homogeneous, which people talk about usually in the books and all other things. Because if they do not consider this medium to be isotropic and homogeneous, then these permittivities will be a space-dependent thing as well. And you have to take the curl of both permittivity and the magnetic field intensity, H. Okay. And what does this isotropic mean? That means if you have a system, let's say this is some material, then if you are measuring permeability using certain techniques, the permeability is going to be same along X direction, it's going to remain same in Z direction, it's going to same along Y direction. Okay. So this will be the exact, I should say, thing that it is isotropic. That means mu of xx will be mu of yy will be mu of zz. This is something called as isotropic. And if it's not isotropic, basically what it is exactly, these permeabilities and permittivities even, they are something called as tensor quantities, and you can represent them as a tensor. You can represent them as mu xx, mu yy, mu zz, mu xy, mu xz, mu yx, yy, mu yz, mu zx, mu zy. This is exactly the tensor, which is basically a permeability tensor. And if you are considering it to be isotropic, then most of these terms will be zero, the cross terms, and the main diagonal term, they will be equal. Mu xx will be equivalent to mu yy will be equivalent to mu zz. So exactly the isotropic tensor will look like, let's say this mu xx value is, let's say 100. It will look like 100, 100, 100, 0, 0, 0, 0, 0, 0. That means the cross terms in this tensor will be 0. That means there will be no component of the permeability along xy direction, and there will be no dependency of those components on each other. Okay, there'll be only this main diagonal component. As a result of which, when you apply the curl to it, it gets simplified. You don't have to basically apply the curl to the permeability and the permittivity if it is in some other equations. But in real scenario, when you are going to the higher domains of the physics, you no longer have this permeability as constant, or you no longer have this as isotropic. Most of the time it's anisotropic and you have to apply the curl to permeability as well. So that's simplistic scenario which people mostly deal with. Let's not go more into it here. We can basically talk about it. Now, if we have a uniform plane wave traveling in a glass with the refractive index of epsilon r and plus z direction of the wave propagation. If let's say this is a glass slab, it has a refractive index of 2.31. Not a refractive index, it's the relative permittivity. It's the relative permittivity. Okay, and let's say this is plus z direction. But actually this, you know that this relative permittivity is related to refractive index. Okay, it's something like a square root relation. Something like n equals to square root of epsilon r. Okay, so the refractive index and permittivity are basically related. And basically you can write the electric field amplitude. So there's an incoming electromagnetic wave with the electric field amplitude of 10 volt per meter. Okay, the wave impedance of the glass is, so you need to find the impedance of the glass. Now, what is the impedance? The impedance is that what uh, basically what sort of a behavior will happen to this electromagnetic wave at this interface. Why? Because electromagnetic wave was traveling in the vacuum with the refractive index n1. Now it's entering the glass slab of refractive index n2, and this n2 is basically determined by the relative permittivity. Okay. Now we need to compute the impedance of this particular, I should say, the wave impedance of the glass. How we can basically do it is we can write the impedance of the glass as the intrinsic impedance divided by the square root of epsilon r. This is basically the characteristic impedance of the free space, and it's around 377 ohms. Okay, I guess you can take a ratio of epsilon divided by mu, and you get this particular value. And this is basically, this is the a sort of the impedance present by the air or the vacuum to the, I should say, uh, I shouldn't say air, I should say vacuum. This is the, because electromagnetic waves can move in vacuum. So this is the impedance presented by the vacuum or the free space to the electromagnetic wave propagation. That means there is an impedance Z1 here, and inside there will be impedance Z2. And at this particular interface, the electromagnetic wave is going to have a different impedance. It will either get reflected or will get transmitted depending upon the reflection coefficient. And that reflection coefficient is basically computed as Z1 minus Z2 divided by Z1 plus Z2. Now, what that Z1 and Z2 is, that's a different question altogether. but most of the time it's computed as difference in refractive index, as you might have seen from your basic courses. So this is the reflected wave from the glass slab, the reflection coefficient of the glass slab. Okay, now what we can do is that we can solve this simple equation to find the impedance of the glass, which is 377 divided by square root of 2.31, and it is going to give you a value of 40.3 amps, 40.3, did I write it correctly? Yeah, it is going to give you 248.04 ohms. So this will be the exact impedance of the glass. So basically what we are computing is what will be this Ng, which is the impedance of the glass. This is exactly what we are computing. So if this was a glass, this is a free space, electromagnetic wave flowing. This has an impedance of 377 ohm, which is called as intrinsic characteristic impedance. And the impedance of glass is basically this thing, which we have computed. That is exactly 377 divided by square root of epsilon r. So this is around 248.04 ohms. Okay, if you want to compute the reflection coefficient, you can compute it by these values. You can write reflection coefficient as 377 minus 248 divided by 377 plus 248. If you compute this value, you will get some value. Obviously, it will be less than 1. Okay, and because this is always in this range, so because the denominator is higher, you will get a value which is close to 0 point something. Okay, that will give you an idea about how much part of the wave is basically reflected. It will be small. Why it will be small? Because you might have seen when you are shining a light on the glass slab, it undergoes refraction, not this much refraction, and then it comes back. That means most of the electromagnetic wave travels and gets transmitted, but only a small fraction of the electromagnetic wave is reflected. That is given by this reflection coefficient. Okay, and we don't usually consider this because we are mostly concerned about the transmitted portion of the glass slab. But if it would have been a mirror instead, then the electromagnetic wave going to the mirror will get reflected, and the reflection coefficient most of the time is around 0.99 here. Okay, that means 99.9% of the wave gets reflected. And it's also negative. That means there's a phase flip of pi. It's sort of a, if electromagnetic wave going like this, it will come like back like this. That's the simplistic scenario. Too many details, I guess. Now, what is the other part? From the data, the magnetic field amplitude in I should say milliamps per meter is you. So in the previous question, we were given electric field amplitude, but we didn't use it anywhere. Why? Because there was no use of it, and we had to simply obtain the impedance of the glass. Now we can use it. How we can use it? We are basically have to compute the I should say magnetic field amplitude. We know that the ratio of electric field amplitude to the magnetic field amplitude is basically it basically gives us the eta g value, which is basically the intrinsic impedance of the glass. Actually, the velocity of this particular electromagnetic wave is given by the magnitude of E over H, the amplitude of E over H ratio. But you can basically link it with the eta g, which is exactly the electric field amplitude. Let's write it EX0 divided by magnetic field intensity, magnetic field amplitude, XY0. So you can take XY here, you can write it as EX0 divided by eta g, which will be basically 10 over 248.04, which we found here. So this will come out to be equivalent to 40.3 milliamps per meter. That this is the exact value of the magnetic field. That means it sort of looks like a wave which is having the electric and magnetic field components. This is the magnetic field showed in the red. And the essential feature is the magnetic field is, where is it? HY0 direction. And the electric field is Ex0 direction. And obviously this is sort of a perpendicular to each other. And if it is a transverse electromagnetic wave, then it should be perpendicular to the direction of propagation. That means it should be in this direction, Z direction. Because the electric field is in X direction, magnetic field is in Y direction, this propagation should be in X direction, sorry, in Z direction. So this particular amplitude is basically 40.3 milliamps per meter inside the glass. And this was around 10, 10.10 volt per meter. That's exactly the scenario which is basically shown in the question. So the answer is 40.3 milliamps per meter. And okay, ampere per meter, yeah. Ampere per meter, that's basically the unit of H. So it's not B, which has a unit of either Tesla or Henry. It can be Henry or it can be even Tesla. I guess Henry is this particular thing, but this has a unit of Tesla, but H has a unit of amps per meter. Okay, that is the fundamental difference, which is basically current per unit area. Exactly. Okay, so now again a simplistic question. From the given data, the uniform plane wave equation. You need to find the plane wave equation, but this wave equation is in terms of the magnetic field. You can write it in terms of electric field as well, as sort of a magnitude of electric field, e to the power j theta. But you can write it in terms of magnetic field as well. You can write it in terms of both quantities. What we need to find is which of the quantities exactly represent it. So one thing we noted is that the electromagnetic wave is going in the z direction. So this is the exact z direction. And you need to basically find the what basically will be this. For example, it will be h will be some magnitude of h, which will be the amplitude of magnetic field. Then it will be e to the power minus j. What is this theta? It is some j. You can write it in terms of jkz, but you can write it in terms of basically e to the power. What is happening to this? E to the power minus j 2 pi over 2. You can write it in as a beta k naught z. But this is 2 pi over. No, it's not exactly like this. Let's write it more generously. E to the power j theta. But this theta can be, if you can write a electric field amplitude in terms of e to the power minus j omega t minus kz, you can similarly write this as e to the power minus j omega t minus kz. That means you have uh, let's not consider this part here. Let's consider h e to the power minus j k z value, and now you have the what is given. You have this particular value here, which is basically epsilon r. You need to consider it here if it is a medium, because there's a medium here. So you can write it as h e to the power minus j, but there's a square root of epsilon. Why? Because actually the refractive index gets inserted here, not the not the permittivity, because the refractive index is square root of epsilon r. So it's basically is h e to the power minus j n times k z, which is basically refractive index. So you can write it as h e to the power minus j square root of epsilon r k times z. This is h e to the power minus j square root of 2 point whatever is value 2.31. This is 1.52 kz. So this is the exact answer, which is basically a simplistic one. And now the final question, which is sort of a cakewalk. I don't know if it needs explanation. We need to just match the following equations, and we need to see which one is which. So this one you can directly identify. It's a Gauss's law. It's a sort of The divergence of the electric field displacement vector depends upon the total charge density. Okay, and this is basically charge per unit. It can be per unit volume. This is charge per unit volume. Okay, with the charge present uh, inside the enclosed surface. And but all of these options have for E, so we need to find another match. We can find it if we have the continuity equation, which is basically the divergence of the current, which is basically the change in the uh, charge density with respect to the time. So 2 should be A. So 2 should be A, this and this. And then we have Faraday's law, which is basically the D part. This means 3 goes to C, 3 goes to D. That means this is the only option. I guess the professor has discussed about this. I don't need to go into the details again. So this is basically the continuity equation, and this is the I should say Faraday's law, Gauss's law, and Ampere's Maxwell equation, which is basically this is the displacement part which Maxwell introduced, and this continuity equation comes in diverse fields as well. This is sort of a uh, it comes in it's not only limited to the electromagnetic fields, it's applicable to all of the fields, whether it's fluids. Even in fluid mechanics, people talk about these continuity equations. Even in semiconductors, you can talk about this continuity equation for the electrons, now because they are charges. Even if you talk about any of the motion itself, then you can write a continuity equation for it. It's just a universal in all the interdisciplinary fields. And it depends upon what flow you are basically talking about. If you, let's say, have a pipe, then you have a water flow inside it. You can again study it using the equation where this will be the current density, which will be the current with the water current flowing through the pipe. Okay, and then there will be this will be the volumetric density of that particular water inside this particular pipe. And you can study the dynamics in the time and space, and there are sort of simulators present online, even in the code, which basically give you the motion and the dynamics of those molecules in time and space inside the this water pipe. So that's the as simplistic scenario. And I guess we are done with this today's session. We overshooted because we lost the connection today for a couple of minutes. That's why it took a long time. And this session is usually fast for these 2 hours, but that's why the lectures are basically uploaded on the YouTube to ensure that you can just steadily watch them and you can slow it down as per your speed. And that's it for now. I hope we can just meet again on during the week 4 session. And that's it from my side. I guess the lecture was supposed to be yesterday, but I shifted it to today because I was not feeling well. I was sick for a couple of days, and that's why my brain is not right now functioning fully to its maximum capacity, and I'm sort of lagging in understanding still some of the things, and I had to put some little more effort. But I hope things go well, so we can meet on next week. Okay, I'm ending the session now. Bye bye.